So, hi, my name is Nicholas and this is Kevin, and we're here to do this talk for you. So, just to make sure we're all on the right page, we're in the Embedded Development Dev Room, and we are here from the Robotics Association in the beautiful city of Aachen, which is very rainy sometimes, and we're here to do this talk about this logo, and my handle on GitHub is Salkinium, and this is eKiwi. So, let's first talk a little bit about my life. So generally, I'm an embedded developer. I develop software on microcontrollers, so it's extremely low level. And this is essentially my story. So I find a new microcontroller, it's awesome, and I think I'm ready to take the next step. So I go through all this documentation, and then finally I get to write some code. And then this new microcontroller comes along with new features, and the same thing happens again. I have to crawl through all this documentation, and then I write some code. And essentially what I've done is I've expressed the same task in different code. And this is obviously a bit stupid, because as a computer scientist, you're like to not work at all, preferably. And so the motivation here is to preferably write identical code for multiple microcontrollers. And if you've read through a lot of microcontroller documentation, you find out that there are a lot of similarities between microcontrollers. And we've essentially compiled all of this into a nice library and added some goodies like object-oriented features, and it's written in C++, and you can write almost identical code on multiple targets. So let's talk about the structure. We're first going to, we're not going to go and tell you the API, because that's really boring. Instead, I'm going to talk a little bit about concepts and explain in some one-line code examples how we actually implemented that. And first of all, we're going to talk about concepts and the interfaces of xpcc. Then we're going to talk about how we use these interfaces to write drivers for external hardware. This is low level, so it's not, don't confuse this with Linux kernel. We're actually talking about low-level stuff here. And then Kevin is going to take over to talk a little bit about the magic behind all of this, our build system, and about the current state and the future work. So there is a lot in xpcc that we're not going to talk about. I personally think of it in three parts. So we have very generic code that can run on pretty much any platform without any change to the code, such as root finding algorithms, matrix multiplications, workflow stuff, and then protocols as well, communication protocols. And then we have things where you need to kind of know what pin to connect to what other pin. So it's more hardware near, and obviously our peripheral interfaces, which we're going to talk about. And then there is the hardcore low-level access, where you actually have to look in the datasheet and access registers. And we're going to talk about these three lower layers, in particular the independent peripheral interfaces. So let's talk a little bit about how a microcontroller looks like. That's how it looks like. It's a black box with lots and lots of pins. And for some reason, these pins must be there. So I could assume that they're used for some sense of intelligent input-output. And yes, that's true. So in general, you can say that every microcontroller has at least this functionality. You have some form of input, you can read it. It will return a 1 or a 0, depending on how you configured it, whether it's high level or low level. And you can do the same by setting an output. And this should actually be satisfied by every target out there. And this is the first example of such an interface, which you can do on every microcontroller. So the traditional way of implementing this is using a function call, where you do all this functionality serial module in your microcontroller. You need to connect that to the outside world. And you can do that in the pin class. So we have this nice connect method, which we get free type checking at compile time. So you know it works even before you applied it to your code. Of course, you never know if it works because you're not a good programmer in general. But the cool bonus is you know what you did because it's there in your code. You don't need to write a comment. It is there in your code. It works. There is no other way. So this is this GPIO interface is available on all these targets. The xpcc framework works on the AT-Tiny, AT-90, AT-Mega, X-Mega, blah, blah. And also on 8-bit microcontrollers and on 32-bit microcontrollers, which is actually quite neat. And if you apply the same logic of finding the most common interfaces, the most common code for all these interfaces, you can see that there are a lot of interfaces which all these microcontrollers support. So I2C, the serial interface, obviously. You have SPI and something that we use to communicate inside our robots, the controller area network, which is also used in cars. And let's talk a bit about our relationship here for a second. So I'm a computer scientist. Well, I study computer science, and he studies electrical engineering. And I come from a human-computer interaction background, and I'm always bickering about usability, and he's always going on about efficiency, and that's essentially what we end up with. So I want to tell the system what I want, and I don't want to look up the data sheet and find out exactly how to do it, because I'm lazy. And I'm going to explain to you what I mean by this. Don't do this. Just please, for God's sakes, don't do this, ever. Like, I have no clue what the baud rate is. In fact, you force me to do this, to go through all of these documents, find out what the system clock rate is that my chip is currently running, find out how the algorithm works, and I still have no guarantee that this actually works. So, this is a bad idea. In general, the solution to this is to compile, is to calculate the settings at runtime. And that's okay, but you have no way of knowing whether the value that actually results in this is actually the value that you put in there. So, for example, in this example, it's not the baud rate that's in your code. It also wastes time, because and space. So instead, what we do in xpcc, we move the calculation to compile time using template magic and const expression functions. And this still doesn't exactly solve the issue of knowing whether that value actually is the value that you get out, but at least it's efficient, because the only thing that is stored in your program code are the actual register values that you then copy into the register at runtime. It does some basic checking, like whether it's even possible. If you have a very low baud rate, the prescaler might have an underrun, or a very high baud rate, it might be an overrun or an underrun, depending. And you don't need to open a data sheet because the intelligence is actually in the function call. And it's, as I said, it doesn't solve exactly the issue of knowing whether this is the value. That's why we added a tolerance. So you can, this goes back to what I said, you can declare, I want this baud rate and I want this exact tolerance. And if this is not achievable, the compiler will throw you a warning, or an error, actually an error. And you can see that the compiler calculates the nearest possible baud rate using the current configuration of the clock tree, of the prescalers, and it will give it to you. It's not as beautiful, unfortunately, because in general, template errors in C++ compilers are not beautiful, but it's better than nothing. That's what we get. So that was an example of how we think about these interfaces. And now you might be asking yourself, why do we use these interfaces in any case? And obviously, as I said, microcontrollers have a lot of pins, and you generally want to connect something to these pins. And in this case, it's an inertial measurement unit. And the question is, can I write this driver to be platform independent? Who here thinks yes? Raise your hand. Okay, that's too little people. So yes, you can, because you must think in protocols. This is a defined protocol. It's a distinct chip, and you can write a platform-dependent driver, because we already have these interfaces. They speak these protocols, and you can build your hardware drivers on top of each other. And that's exactly what we've done in xpcc. this is essentially what we've done. So you have your you have 3 devices on your I2C bus, and they only talk through this interface. And the driver doesn't care whether on what platform it is, because the interface is always satisfied the same way. In fact, you can even write a software emulator which then uses the GPIO classes to be truly platform independent. So that's what we've done. Also, we don't have time to talk about this, but there's an added tech point bonus. The entire API is, well, not the entire, but at least for I2C, is non-blocking and callback based. So it's really fun to write these drivers. And now Kevin will talk a little bit about the build system. He's smarter than I am.
Okay, so let me go on and just take you from where Nicholas left you. Let's go a little bit back to the black box again. And as an electrical engineer, I make some observations. I can see that there are all those pins, and those pins don't change once the chip is produced. So that's what I call static. Nothing changes during runtime or in your product. And also, if you go a little bit under the surface, here you see this is a block diagram of an STM32F4, and you can see there are all those different interfaces, or all those different peripherals connected to a bus, and they don't change. You don't get added interfaces, or they don't, I don't know, they don't leave the chip during runtime. So what I'm getting at is that we want to model this in software, and what comes to mind when we're using C++ is using static classes. So classes that only have static methods, that only have static members. And what this gets us is that, or what we're getting at with this, is that you have all those peripherals, and we want to generate a class from every one of those. So now you say, well, this is a lot of things to do. Why can I not just have like one UART class and then give it the index and say like, create a new UART1? Well, this is a little bit error prone, because you got to imagine you're running on a microcontroller, so there's no way to report errors. On your regular system, you can just, I don't know, like do an assert and your program crashes and there's an error message or whatever. But on a microcontroller, you have no good way of telling the user, well, there's something wrong. So if the user creates a UART with a wrong ID, it will just not work, and the user doesn't know why. If we have a class for every UART, he can only use the classes that are provided. And also, it's a little bit more efficient to use static classes, because you will never have to calculate any offsets in memory. So now, we know that we want a static class for every peripheral, but there are certain problems. One is that we need to know for each device that we support, for every microcontroller has different peripherals. So we need to know what peripherals are supported on our device. And that's why we came up with the XML device files. What you can see here is that we got the file for an STM32F407 in its different variations, and it can tell us what kind of memory the device has and what kind of peripherals it uses. We're actually creating those XML files through a process through a script that we wrote from the manufacturer information, so that's pretty easy to get that. And you can also adjust it by hand if there are some problems with it. And then here we see that we have the peripheral. It has UART, and that tells the build system to search for the UART driver, and the UART driver has an additional XML file that tells the build system what kind of files it needs. So now we got another problem. We're all developers, we're all lazy, and we don't want to write duplicate code. Like I said, we would like to have like one basic template and use that to generate all the UART classes, for example. And that's just what we do. We got all those in files, which are our template files, and we generate all the UARTs that we need. And to do this, we're using the Jinja 2 template engine, which comes from web development, but it fits the thing that we need quite neatly. And also, one cool thing that we can do is we can check what kind of target we're building this driver for. So for example, if one manufacturer normally uses the same peripherals for every controller that he puts out, but they change certain subtle things. Like for example, they renamed the data register to transmit data register, or they added a transmit data register for the F0 and the F3, which are actually the newer ones. And so here we can do checking and see which kind of register we need, so we don't need to write a whole new driver for them, but we can just do some basic checking in the template. And so our build system is based on sconce, which is a build system that runs with Python, so it's easy to extend. We have a lot of custom Python scripts that do all of this, that do the lookups for you, that generate the drivers for you, and it even tracks dependencies. So if you change a template file and you construct your program again, you don't remake it with that, but you construct it or whatever. And so when you do that, it realizes, oh, the template file has changed, so I need to regenerate all those header and C++ files and compile them again. So that works quite neatly. And so when we want to, for the long term, we want to reach a little bit further and generate the whole xpcc library. Right now, we're just generating the peripheral drivers, but we want to make it possible to have a library description, then select all the drivers that you want. You've seen there are all those different layers that we cover with our library, and you might not want to have all of this in your library. And then you can get a custom library, and that also fits embedded development quite neatly, because with the microcontrollers, what you want to have is, for some companies, they have their custom build system, so they want to use xpcc with their custom build system. But since we're doing all those template stuff with all those thousands of lines of Python, they cannot just use our library. But if we do this, they generate their library once, and then they can use it with their custom build system. And also, you can just put it in a zip file or check it in internally, and I think that fits the way embedded development, at least for microcontrollers, still works a little bit more nicely. But in the meantime, there are some more near-term goals. It would be great if any one of you ever wants to have a look at xpcc and maybe use it in your project. A good way to get started is to get one of those STM32 F4 or F3 discovery boards. You can get them pretty cheap from ST, and we have good support for them. You can just check out xpcc, go to examples, go in the folder that's named after your board, and then you have all the examples that you can just use, and you can just use sconce program and just put the code onto your board. Also, if we need to improve our documentation, and if any one of you ever has a look at our library and says, well, okay, that's neat, but it took me a lot of time to find that out. If you want to write a blog post about it or whatever, we can always include that in our documentation. Also, if you're getting started with xpcc and don't know what to do, a neat thing to do is maybe write an IC driver and then maybe do a pull request or write on our mailing list and say, hey, I did this IC driver, can you integrate that? And we're always happy to do that. Also, if you want to add, if you have one of the STM controllers, for example, and you want to add an advanced feature, just go ahead, have a look at the other peripheral drivers and try to add one yourself. You can also just ask questions on the mailing list if that's a problem, if there are problems. And also, xpcc can be ported to new platforms. Almost any platform that has a GCC compiler, you can get it running pretty easily, or a G++ compiler. For example, there's some support for the K20. If any one of you is working with that, we have a branch that's called machack. It's not in a good state, but there is a little bit of support for the K20, and also support for LPC. There's a little bit, but there's not much for the Atmel ARM devices, and for the MSP430 should all be possible. So if anyone is interested but says, well, I don't like the ST devices or whatever, it's not that hard to port, and we'll be happy to support you. Yeah, so that's what we support right now. We support Linux and Mac OS X as host OS. If you want to try, you can also try to run this on Windows, but I don't think anyone here cares really. And here the boards, the STM32 discovery boards work best. The LPC, we have for one LPC board, you can just check out our examples and see what kind of boards we named there. One of the LPC boards work pretty well, and we don't have any Arduino, but the stuff works in AVR, so it should be pretty easy to run that on an Arduino board. And yeah, you can check us out our library on GitHub, or just write an email to our development list. We're always happy to answer any questions.
Also now.
Yeah, right. If anyone here has questions, yeah, up there, the one right there. Yeah, you're the one who's.
So you have a script where I import the PDF from the manufacturer and output C++.
No. Some of the manufacturers release XML files. Oh, you want to say?
Yeah. So here's tethered to me. The ideal. Actually, the idea was to write these device files by hand, and that's why they're very simple. But if you have 200 devices, this gets kind of tiring. So I found some obscure files on the internet that describe these things in memory mapping and stuff, and then I just wrote a Python script that gets all this information out, compresses it a little, and then you can have these compressed, nice device files. Not compressed in the sense of compression, but it aggregates the information and displays it nicely. So
that means basically I can't use this in industry because you don't know where these obscure things come from.
that's nice because you don't have to know, because we give you the device file, so there is no licensing problem.
And actually, yeah, I mean,
we generated them.
You can, if you have, we're still using the header files from the manufacturer.
Yes.
with the register layout.
Yes.
So if there's something in the header file that doesn't, if in the files that we use as our source, if that doesn't exist, it just won't compile. So you will just notice.
Yes.
What license are you providing this?
2 class, 3 class, 2 class BSD.
BSD license.
Using xpcc,
Yes.
writing generic code in C++,
Yes.
as opposed to bad old C.
Yes.
Is there an overhead in terms of code size?
Yes, I anticipated that question.
Can I answer it?
You can.
Oh yeah.
Sorry.
So you got to compare different ways of doing stuff. For example, what I do when I got started with a new driver, I just added a DMA driver for the STM, and what I did first is I wrote everything to a register. So that's like the smallest that you can get to in code size and stuff, because it all pre-calculated and just writes one value to it. And what I did then is I added like 3 methods to configure the DMA, because I thought it would be useful to have like a general configure, then connect to a source, connect to a sink. So what it does then, it like every method is on its own. So what it has to do, like there's one configuration register. So every like the calls after the first configuration, you gotta read back the configuration register, then just change the value that you want and write it back. So there's a little bit of overhead in code size. For example, it added 65 bytes. What I did, but what you have is, especially the critical stuff, is what the things that are called a lot of times. For example, the GPIO set, set and reset, and that actually just compiles away. We put a lot of stuff in header files, which does not necessarily benefit compile time, but it's not that much, so it doesn't really matter. And so what you get, for example, on AVR, you just get a simple assembler command that just sets your port high. So it's a little bit of overhead compared to writing registers on yourself, which is kind of ridiculous for those big devices. But if you compare it, for example, to a C++ library that doesn't use link time optimization, our stuff is most of the time it's better, because we use a lot of static stuff like templates, and we try to use like inline our code.
I want to say something.
You want to add something?
So for normal people, to translate that, essentially we use static stuff. So we try and think about function calls. So as he said, most of the code is in header files, and we do aggressively inline manually. So for example, if you only set a bit on a register, the entire function is inline, because you can't do a function call in less than it doesn't work. So we have to manually optimize this sufficiently. So we do use certain features in C++ that are an overhead, for example, virtual function calls, which are two dereferences on an ARM core, but on an AVR there are more calls because the bus is smaller than the addressing. So there are certain things that you need to know in order, but it's still a compromise between software engineering and efficiency. But compared to traditional C programming, it is actually quite efficient. So we don't we don't allocate memory just because we need a new class. It is there. That's, I think, the most important stuff. Do we have to?
We have to finish now.
Right?
Thank you for listening.
Yes.